This video is to go through the 2017 AP Calc BC free response questions. So the first one wanted a left-hand Riemann sum. So we have our gap between our h values is 2 times the left-hand y value is 50.3, and then same idea for the others. The calculator ones, you should be able to just sub it in, get the 176.3. Now we were doing a square feet times a feet, so our units on that should be feet cubed. Riemann sums left hand, right hand. You determine overestimate or underestimate based on if it is increasing or decreasing, because no matter if you're decreasing in concave down or decreasing in concave up, when you do a left hand sum, it ends up as an overestimate. Concavity would come into play in terms of over and underestimates if you're doing a trapezoidal rule. For the next one, we are just doing an integral. The expression they gave us was for the square feet, and the dH turns it into a volume. So basically that's the volume of one little slice, and then the integral adds up the volume of all of those slices. So we get that 101.325 feet cubed. Next one, our volume equation is V equals 0, integral 0 to h, then put in a dummy variable in your expression. This is a related rates question, so we're going to take our derivative with respect to time. We get dv dt over on the left. On the right side, when you take the derivative of an integral that goes from a number to an algebraic expression, we just sub the algebraic expression in, and then you have to multiply afterwards by the derivative of what you subbed in. That's why we got the times dh dt on the end. They told us that the rate of the height was increasing at 0.26 feet per minute. That's why it goes and has a positive 0.26. Remember to always look for those context clues for those rates, because it won't come out and say it's negative. Usually it'll give you a context clues if it's supposed to be negative. And then also sub in the 5 for your 5 feet, put it in the calculator, and it was a change in volume per a change in time, so we have feet cubed per minute. For 2, we had some polar functions, area of r, so it's just simply our polar area formula. So you have 1/2 integral of the radius function squared, d theta. So I showed the actual radius expression. You could have also just called that f of theta all in parentheses squared. That would have been okay. And make sure your calculator's in radian mode when you're doing this. We get that 0.648. Now in part B, we've got a ray that's cutting through and splitting it in half. There's a couple different ways you can set this up. So what I did first is I did the whole area of S on the left-hand side and multiplied it by a half. So the area of S would be the area, the polar area for g of theta, and then take away the polar area for f of theta. And then I threw a 1/2 out in front of that. So my left side represents half the area of S. And then the other side is that same g of theta getting squared minus f of theta getting squared with our polar area set up. That's why it's got a 1/2 out front. Now just note, for whatever reason, I chose to do on the left side 2 separate integrals of those polar areas with the radius squared. Anytime you have addition or subtraction happening, we could do it as one as well. So on the right side, I just chose to do it as one. So you could either do it as 2 separate or just one. Now the other way you could have set this up is you could have made the right side be identical to what I had. And then the left side, you could do 1/2 integral from k to 2 k to pi over 2 of r g of theta squared minus f of theta squared. So a few different ways that you could set it up. The way they explained w of theta in 2c, it's just the distance between our curves g and f for any particular theta. So think about if you just drew a ray coming out from the pole, and whatever the portion is on that ray from the edge of r to the edge of s, and we wanted to find that length, we would just have whatever g of theta is minus f of theta. Important that we have f of theta in parentheses because the negative needs to apply to all of it. So that's the first part of 2C. 2C is a great example of one where you want to read each part when you think you're done, because individual parts sometimes have more than one thing that they want you to give as an answer. And this one was an example of that. Next, we wanted to find W of A, which was the average value of W of theta. So we do 1 over B minus A, our integral, and then using that expression that we had written in the earlier part of 2C, put it in the calculator, see what you get. And then in 2D, we wanted to know the value of theta that made W of theta equal its average. So in 2D, the left side is just the non-rounded version of my answer in 2C. On the right side, I have my W of theta expression, and then you're just solving that in a graphs page, putting in like theta for x, and you get the 0.518. Now you can simply graph W of theta, which you would have had to do for this problem anyway, and you could have noted that its derivative at 0.518, um, where it's crossing uh, is that the derivative is negative, therefore W of theta is decreasing. All right, moving over to question 3. So when they give you a graph of a derivative and they give you some point on the original function, without even reading the rest of the problem, you can almost guarantee you're going to do an accumulation function at some point in one of the parts. And we do that right off the bat in part A. Because if we want to find what f of negative 6 is, we've got to use the fact that we know that at negative 2, f is 7, and then we'll do the integral of the derivative from negative 2 to where we want, so negative 6 in this case. And that's what's in the handwritten black over on the right. I'm doing that accumulation function. Because when we do our integrals by hand, we like the smaller bound to be on the bottom. We'll flip it and put the minus out front. Then you just did your area of f prime from negative 6 to negative 2, which was 4. So they subtract to give you 3. Now what I didn't show there is for f of 5, we are also doing an accumulation function. We are going from negative 2 to 5. So there's no funky business with having to change the sign or anything, so I didn't show that one. If you do your area from negative 2 to 5, you got a triangle above that had an area of 3, and then you also had the half circle that was below, which gave us that negative 2 pi, so altogether 10 minus 2 pi. Now we are into no calculator territory, so as long as you have any equivalent answer, it is your choice how far it is simplified, provided it is numerical. On part B, if we want increasing, we want to look where f prime is positive. So that would be inclusive at negative 6 going to negative 2. We're including the negative 6 because at the point negative 6 it is above the x-axis in the derivative. And then we have also 2 to 5 as well. And again, that's since f prime is positive. For our absolute minimum, we need to check any local minimums and the endpoints. So for our local min, we can identify from the graph that that's at x equals 2, since f prime switched from negative to positive. At our endpoints, f of negative 6, we already found was 3 in part A, and we found that f of 5 was 10 minus 2 pi in part A as well. Now I just estimated pi as 3.14 to get a sense of what 10 minus 2 pi is, so we will be able to accurately identify the absolute min. And now for f of 2, we will have to start with our value of 7 that we had, and then we'll do our integral from negative 2 to 2 of f prime of x. So we're essentially just subtracting off the half circle. That's how we get 7 minus 2 pi. And again, using 3.14 as pi to estimate, we get 0.72. So because 0.72 is the smallest of those, the 7 minus 2 pi is the absolute min. I would suggest don't say that 0.72 number because that was just an estimate, and it might not be the accurate amount rounded to 3 places. So use the 7 minus 2 pi. And for D, our second derivative, we want to be looking at the slope. So at -5 in f prime's graph, we're going down to and right 4, so we get a -1/2 for its second derivative. At x equals 3, f prime has a corner point, so therefore the second derivative doesn't exist. For a derivative to exist, it has to be continuous, which it was at x equals 3, and your slopes from the left have to approach the slopes from the right. Well, the slopes from the left are a constant positive number, slopes from the right are a constant negative number. Those will never approach each other, so that's why we know the derivative does not exist there. Any abrupt changes in slope would cause a derivative to not exist. For the potato question, we have a tangent line equation. We need essentially an x, a y, and a slope. They tell us that our x is 0 in the question, the y is 91. And to find our slope, take the differential equation and put the 91 we knew for h in, and that ended up giving us -16. So we got h minus 91 equals -16, and that's technically t minus 0 in the parentheses there. So then we sub in the 3 for t, work to get h by itself, and you got 43 degrees Celsius. Our second derivative. The first derivative is technically linear, so that's like a -1/4 h, so its derivative is -1/4, and we took a derivative of an h, so we got to multiply by dh dt. Replace dh dt with what it was equal to, and then fill in the 91, which was our h value at our point of tangency. It gives us a positive, so therefore it is concave up at that value of h. So therefore our tangent line would be below the graph, making it an underestimate. For 4c, we've got to solve a differential equation. So we want to get the g's over on the left and the t's over on the right. So I chose to leave my -1 over on the right with the dt. I divided that parentheses over, so it became g to the -27, g minus 27 to the -2/3. Did integral of both sides, and I chose to put my plus c on the right. Now on the left, that's technically a little u substitution that we're doing, but u would equal g minus 27, so du would just equal dg, no correction that would have been needed there. So I just went ahead and did it without showing the u substitution. Sub in your 0.091, and we get 12 for c. So now we need to get g by itself, so we'll divide the 3 over, then cube both sides, and add the 27. We just want to make sure we don't have to restrict it all. There's no issues with our g of t, and there was nothing with the differential equation either. And then lastly, they wanted us to use t of 3 to approximate our temperature using this function. So put the 3 in, you get 54 degrees Celsius. Moving on to our next no calculator, number 5. Slope of a tangent line is just a derivative, so you've got to do a quotient rule, or you can bring it all up and have it as 3 times stuff raised to the -1 and do a chain rule, your preference. So I did a quotient rule, and then from there, sub in 3 for x, and we end up getting -15/4. Free response, no calculator, so it's your choice how much you're going to simplify it. Anything under there would give you full credit. For part B, we want to know if where our critical values are and if they're relative mins, maxes, or neither. So we already have our derivative from that quotient rule, so I set it equal to 0. A fraction is 0 when the numerator is equal to 0. So I took the numerator, set it equal to 0, and got 7/4, or you could have 1.75. We were on the interval 1 to 2.5, so I put those and the 7/4 on there. When we do our pluses and minuses, the denominator is not going to affect anything because it's squared, so it'll always be positive. So I just thought of the numerator as a line with a negative slope. When you have a line with a negative slope, it's going to be positive to the left of the 0 and negative to the right of it. So we get plus minus. So now we can say that x equals 7/4 is going to be a relative max since f prime switched from positive to negative. In the next one, they gave us how it split up into partial fractions. Then we had to do our improper integral. When we do this, that first one, it's technically as a u substitution. U is equal to 2x minus 5, so du would equal 2 dx. So the 2 dx gets replaced by the du, or you can think of it as there's a correction of a half, however you'd prefer to think of it. But anyway, the 2 essentially goes away, so we have natural log of 2x minus 5, absolute value of 2x minus 5, and then no corrections happening in the other one, so minus natural log of x minus 1. Now, because b is approaching infinity, these insides of these absolute values are going to be positive. I chose to just leave them in there, but once you recognize those insides are going to be positive when b goes to infinity, you could turn those absolute values into parentheses wherever you would like. And then from there, we're going to let b go to infinity. So I used some log laws to bring some things together. And as b goes to infinity, if we look at the ratio of those coefficients in this line here, that's going to end up approaching natural log of 2 because the same degree, so ratio leading coefficients. And then a natural log of 2 minus a natural log of 5/4, you divide your insides, and we get natural log of 8/5. For 5D, our expression was positive when n was greater than or equal to 5 because our summation started at 5. It was continuous and decreasing, so therefore we can apply integral test. We just found in part C that our integral or improper integral gave us an actual number. So therefore that means the improper integral is going to converge. So we can say the series converges by the integral test. And moving on to number 6, they gave us f of 0 and f prime of 0. Sub in a 1 for n to get the second derivative, which would give us -1. Sub in 2 for n in that expression or that equation they gave us to get the third derivative, which was 2. And then your fourth derivative ends up being -6, doing the same thing. So we needed to go to the fourth degree term because there was no function value term, and we needed to show what the first 4 terms were. So do the things we got divided by their factorials. We had a Maclaurin, so we're centered at 0, so it's just x raised to the powers. So we got our 4 terms there, and then plus dot 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 equals. We got to come up with our summation. Notice in the simplified form there, it's just got the denominator without a factorial matches the exponent, and we're starting at 1. So that gives us x to the n over n, and I started it at n equals 1. And then we need positive first, but we're going to alternate signs. So I did -1 to the n plus 1. So when you sub into 1 for n, you get an even exponent for the -1. We want absolute or conditional convergence. They want us to do it at x equals 1. So when you sub in 1 into our general from part A, it's just 1 to the n, so it's like it's not there. So we want to consider the terms as they go, as n goes to infinity. They do approach 0 because the bottom will get bigger, and each term will be less than or equal to 1 before it. So therefore, we can say converges by alternating series test. Then do the absolute value of the series. That becomes 1 over n for our series, which diverges since it's harmonic. Therefore, we can conclude that our series converges conditionally. In part C, if you take the antiderivative and sub in x and then sub in 0, the subbing in 0 just wipes everything out. So it's basically like we're just doing our antiderivative and filling in an x, which is just like doing the antiderivative. So just take your antiderivative of the 4 terms with powers going up 1 and dividing out front by the new power. Then you've got your general term where the exponent goes up 1 to n plus 1, and we'll divide by n plus 1. For the next one, we have an alternating series error bound. They took it out to the 4th degree term. So then we would just have the absolute value of the next term, our 5th degree term for G, which was one of our terms that we had in part C. So just take absolute value of that -1/20th. We're subbing in a half, raising to the 5th, neaten it up, and show it's less than 1 over 500. And it was 1 over 640. And that's it for 2017 FRQs from the AP Calc BC exam.